Okay, our next speaker is Balint Virag from University of Toronto. His main interests are probabilistic geometry, group theory, and spectral theories. He received the Rollo Davidson and Stochastic James Prize. And his title for today's talk is Operator Limit of Random Matrices. Please welcome the speaker.
Thank you very much for the invitation. It's very nice to be here in Korea again. So the title is Operator Limits of Random Matrices. So maybe I'll start in the 50s, where basically the circle of questions that we look into nowadays originated. It was Wigner's idea to find a model which is good for modeling the gaps between the energy levels of large atoms. And you know, the interesting thing is that Wigner sort of tried to do this as a mathematician, not really as a physicist, in the sense that he didn't really care that the inner structure of the model somehow reflects the inner structure of the physics phenomenon. He just wanted to have one that was sufficiently nice math and sort of fit the description of what you have. And of course it was a remarkable success, but it wasn't really right away. So he tried 3 different things before he got to his random matrix model. The first one was some kind of random Schrödinger operator. He also looked into random analytic functions, and finally he got to the Gaussian orthogonal ensemble, or GOE, which was the model that sort of stuck. He has a nice series of papers on this, and mostly in the Annals of Math, and it's very nice that eventually he found the right model that somehow is still used today. So what is the GOE? Well, you just take a matrix M and you fill it in with independent standard normal entries, and then you symmetrize it this way. So that matrix A is the GOE. Let's say an n by n matrix, and here's a picture from Wigner's paper. So if you look at the eigenvalues of the GOE, this is what the picture looks like. And if you draw a histogram, you get this kind of semicircle. This is the first theorem, I think, that Wigner published on this. But he was really interested is not so much on this global shape, but how the eigenvalues repel each other here in the center. And then you can tell that, already from this picture, you can tell that this is not a Poisson process, right? These points are a little bit more regular than points dropped at random, and this is due to the repulsion that's between them, as we will see. So the idea was that if you find the right math model, then it will reflect, it will be a good description of many physical phenomena. And indeed, you know, there are recent surveys, there are at least 20 different physics models that show random matrix behavior, but very little of this is proved. So you know, up till about a few years ago, we didn't even know that random matrices behave like other random matrices. If you changed, you know, the entries a little bit, then they would still show the same behavior. And you know, some interesting ones are if you take a Laplacian of large planar domains, you know, they should also look like the GOE. And here's some picture from the paper where this was conjectured. If you take a random Schrödinger operator in high dimension, where it's conjectured to have extended states, it's also you also believe that there be GOE or GOE. And finally, the Riemann zeta zeros should also, if you look at the random place, they should also look like the mean spacing, also look like the spacing of GOE in the middle. So very little. Again, very little is known for actual universality, where we're looking at models that are not matrices and should behave like, or not just straight out random matrices and should behave like random matrices. One is you know, models in the KPZ class. So you have seen many talks about these, and there are exact maps that relate them to random matrices. Then there is the Frobenius monodromy, which is a number which is sort of analogous to these Riemann zeros in a slightly different world in number theory. And finally, we also have some small results that in the random Schrödinger, when you have some funny scaling, then you can still find these GOE statistics. So you know, given Dyson's original enthusiasm that this is going to be some new statistical mechanics, this is a quote, you know, still mathematically still very little proved. So what I'm going to talk about is not this, but more like how to understand really the structures that are behind these objects. How do you describe this eigenvalue behavior in the bulk? I mean, one description, of course, is just to look at the finite matrix, but that's usually not what's universal. You want to take a limit as n goes to infinity, and you have some kind of eigenvalue distribution. And there is a description for that in terms of correlation functions, but it's fairly complicated. So we're sort of proposing a simpler description, which has a little bit more structure, and also is more amenable to analysis. So what are these descriptions? And the description is basically a very simple idea, is that you take, instead of taking the eigenvalues of your random matrix and then taking a limit of the formulas that come out of that eigenvalue distribution, you sort of try to take a limit of the random matrix itself. And hopefully you get some kind of infinite random matrix, which is an operator, and then you can study that and directly read off some properties. I'm going to show you lots of examples of how this goes. And this is a program that was initiated by Edelman and Sutton, and they proposed many operators that should be limits of random matrices. So you get, hopefully you get a simple description of the limit. Well, it will work for this general beta. I'll tell you about what that is. You know, you keep some nice structure in the limit, which you can analyze, as opposed to just some formulas that are you know, some limits of computations. It can be used, hopefully, for proving asymptotics and deduce exact formulas. And I'll show you examples of all of these. So let's first let's first show how this thing starts. And so let's say we have now a general symmetric matrix A, and let's A be its first, little a be its first element. So let's write this in this block form. And first we're going to conjugate this matrix so that it's upper triangular, so that it's tri-diagonal. And here is how you can do that. So if you take an orthogonal matrix of this form, which is, again, there is a 1 by 1 block and there's an n minus 1 by n minus 1 block, and you conjugate the matrix by this, then this is what you get. That's the result, and you can choose your O in a way that only the first entry of OB is non-zero, right? So by this conjugation, you manage to zero out everything here in this column, and you can then continue to get a tri-diagonal matrix. That's the Fri-Diagonalization argument, and it's nice because you did very simple operations, and you reduce the dimension of your data from n squared to about 2n. So this you can do with the GOE. You can do it by hand. It works very well. So in the end, you get this tri-diagonal matrix with entries AI and BI, and you can write down exactly the distributions. The AI, the distribution doesn't change from the original. They remain this normal 0, 2. And the BI are going to be, well, there's basically these Gaussian vectors that are rotated into one coordinate. So they're just going to be the length of the given Gaussian vectors, which have chi distribution. And this is what the chi distribution looks like for large values. So it's approximately the root of its parameter plus a normal of its variance 1/2. So the Trotter's theorem says, basically proved exactly the way that I was showing you, is that this matrix J has, if you have a tri-diagonal matrix J with these entries, then it has exactly the same eigenvalue distribution as the Gaussian orthogonal ensemble. So now you have this nice J, it's an operator, it has a little bit more structure than your matrix. And we're going to take some limits of it. They're going to be operator limits. I know 6 different kinds of limits that you can take. There are probably more, but I've counted 6, and I'm going to show you 4 of them. So hopefully the first will be very easy, and they'll be sort of more complex as we go on. So brace yourself. At least if you get lost on one of them, then you can get back in the next one. So So here is the set of eigenvalues of your original matrix A, or the GOE, and here is a schematic picture of your tri-diagonal matrix. Like you can think of it as a weighted adjacency matrix of a graph which is a path plus some loops, and the weights on the path are this B, on the edges are this B, and the weights on the loops are this A's. So that's one way of thinking about it. And properties translates from one to others, one place to another. So by studying this, certain properties of this thing, you can deduce certain properties of that thing. So for example, the global behavior of the eigenvalues will correspond to local behavior of this operator J at a typical location, so somehow a random location. I'll make that more precise. You can also say something about global behavior of the eigenvalues by just looking at one of the ends, for example, the right end. If you want to understand the fluctuations of the eigenvalues now in the GOE, so on the edge, here or here, one of the edges, then it turns out that what you have to look at is the top part of this operator J up to about n to the 1/3 entry. So that's the window that you have to look at. The others actually don't matter at all. And finally, if you want to understand the local fluctuations in the bulk, then you have to look at the global structure of this entire operator. Okay, so there is some kind of local and global reversal when you look at this. So let's do some linear algebra. Okay, just standard stuff, but it's not as standard, so I want to define it. So I want to define, if you have a symmetric matrix, what is a spectral measure at a vector? Okay, so you could define it as the unique measure for which, if you take this inner product of the vector, then it's going to give you the powers of the moments of the measure, right? So if you think of this in terms of a graph, then you, if A is an adjacency matrix of the graph, then you're just counting, and E is a coordinate vector, and you're just counting paths of length k from E to E. Yeah, that's an example, but generally you count paths with weights that are products of the weights on them. So that's the formula, and there is a more in the case of finite matrices, which we're looking at, there is a simpler formula, which is, this is a finite measure which puts masses, delta masses at eigenvalues, so it lives on the eigenvalues, but it's not just the ordinary eigenvalue counting measure, it's a kind of a local version. It looks at this vector E, and you square the inner product of phi I and E. You can also define this with spectral theory, but I don't want to get into that. So now if you take, for example, E to be a random coordinate vector, then the expectation of the spectral measure, if you average let's say if you average the spectral measure over all the coordinates, then because these eigenvectors, these phi i's are the eigenvectors, they're orthonormal, you get actually the eigenvalue empirical distribution. So it's some local version. Again, if you average over all coordinates, you get back the empirical distribution. So this definition also works in many cases for A that are infinite. So if you have an infinite matrix, you can, so some technical issues, but most of the cases we look at will be able to define the spectral measure for infinite A. Okay, because if you can compute this thing, then you can just hope that there is a measure for which these moments are the right thing. Okay, so that's spectral measure, and let me talk a little bit about Benjamini-Schramm convergence. So we're looking at graphs that are converged, and we're also looking at their spectra, and by that I mean the spectra of the adjacency matrix. So there is an edge between two. There is a 1 in the matrix if the corresponding two vertices are connected by an edge. To talk about, so this is going to be our first example of operator convergence. So what I want to do now is give you a proof of the Wigner semicircle law. So this is not a very new thing, but it's. I hope that you will like this. This is a proof that doesn't have any computation. Okay, so this will be a proof of the Wigner semicircle law. I was a little bit hesitant actually to give it because this is the ICM after all, and you can just prove the semicircle law in an ICM talk. But then 2 days ago, Sasha Sodin, he proved the CLT for coin tosses. So I said, okay, I can do this too. It was a beautiful proof, by the way. So, okay, so a sequence of graphs converge locally. So again, it's a sequence of rooted graphs. We say they converge locally if for every R, the R neighborhood eventually stabilizes to be that of G. Okay, so you look around look around this root R, root O, and eventually what you see is going to be the same as in this is G. You can extend this to weighted graphs in which the weights you also require them to converge. They can be real weights or something. So and a simple example is when you take the n cycle, right? As n goes to infinity, it converges to the integer z, the integer lattice z. And if you well, of course, this implies that, remember, the spectral measure is just counting paths around O. So because of the stabilizations, the moments also stabilize for the spectral measure. So it tells you that the spectral measures converge, okay, weakly and in moments, to when you have this local convergence. So one implication of that is that the spectral measure of Z at any vertex, because of course it shouldn't depend on the vertex because this is translation invariant, is the arcsign law on -2, 2. Why? Well, you know, the spectral measure on the n cycle, you know, because it's just the sum of a shift plus its inverse. And of course, the eigenvalues of the shift are just the roots of unity, right? So you take the roots of unity plus their inverse, or plus their conjugate. So it's twice the real parts of the roots of unity, right? So twice the real parts of the roots of unity converge. So they're basically almost uniform on the circle, right? So what you get in the limit is a measure that is uniform on the circle, and you project down to the real line, right? And that's the arcsign law. So this is just a simple proof for what is the spectral measure of Z. So now let's see, if you have a sequence of finite and bounded degree graphs, now not rooted, okay, then we say that they converge to a random rooted graph in the Benjamin-Isham. These are not random and not rooted, and the limit is a random rooted graph, okay? In a Benjamin-Isham sense, when you take a uniformly chosen random root in Gn, okay, then this random rooted graph converges to GO in distribution in the local convergence that I defined before. So what does that mean? It basically means that if you pick a random place in the graph, then what you see around yourself, the statistics of that stabilizes, okay? And it stabilizes to not the actual what you see, but the distribution of what you see, and it stabilizes to some kind of random rooted graph in the limit. Okay? So of course, if you have this, then you also have in distribution that this random spectral measure converges to the random spectral measure. And that means that then also the expectation of this spectral measure converges to the expectation of the limiting spectral measure, right? You can just take expectations of the statement. But you see the first time the expectation of the spectral measure at a random root is just the eigenvalue distribution, right? So because we have seen that. It's just the average over a basis of this spectral measure, and we have seen that that's actually just the empirical distribution of eigenvalues. So we call that mu g, and so this mu gn converges to this quantity, which is the expected spectral measure of your limit. Okay, simple. So here is now a proof by picture. Okay, so I want to prove the Wigner-Semicircle law by picture. We're almost done there. So let's see. What does this graph look like? Okay, so this graph has these weights. The A's are normal 0, 2, and the B's are roughly some square root of n plus some little noise. So if you take this and divide by square root of n, which I didn't write, but I should have, okay, to divide all the weights by square root of n, then what will you see at a typical place? Okay, well, at a typical place, this noise won't matter because it's too small. For a large n, you won't see it. All you see is the randomness that comes from choosing the place. Okay. Because these means they range from 0 to root, so from 1 to root n, and when you divide by square root of n, they range from 0 to 1, and they converge, the distribution converges to the square root of a uniform random variable. Right? So then you have this, the limit, the Benjamin-Isham limit, almost surely actually, is going to be this graph, which is just a copy of z with a random weight. And what is this random weight? It's the same weight everywhere. It's not independent copies. It's just the square root of a uniform. So this is the operator limit of this graph if you take it in this particular sense. Okay? So it's just the square root of a uniform times z. And now we're basically done with the proof, because you see you have you have the arcsine law, which is just the projection of the semicircle to the line, and now you weight that with the square root of a uniform. So basically pick a radius with this distribution, and then you look at the length measure on the corresponding path, and of course that is just the measure on the semicircle projected down to the real line. Okay? So that's the proof. Is that really a non-computational proof? I hope you buy that. I actually have been asked this question of how do you relate the semicircle distribution to the arcsine distribution, and this is one answer to that. By the way, this is essentially Trotter's proof, but it's just said in a different language, so somehow in a non-computational language. Okay, so that was the first operator limit here. Okay. Now, what we're gonna, I want to introduce this beta Hermite ensemble. So this is I'm going to go to the second picture. So I'm going to tell you about this Fri diagonalization that we did in a completely different, from a completely different point of view, but it's going to be actually the same thing. So you won't really recognize it, but it's pretty much the same. So that, again, we take a symmetric matrix A, and we look at this, the matrix applied, the powers of the matrix applied to a fixed vector A. Okay, so this gives you a sequence of vectors, and you assume that these form a basis. Okay, and then you take J, which is the matrix A in this new basis. So it's A conjugated by some orthogonal matrix. Okay? So it's a simple fact. You can check it that J is going to be a tridiagonal matrix, and you can set the BI to be 0, or if you do it right, it will be automatic. Sorry, the BI to be greater than 0. These of diagonal terms. And notice that since O, we took the first basis vector to be E. Okay, that didn't change. This O fixes that vector, okay? And so that means that these powers are the same, okay? So these inner products are the same for A and G, because the O fixes E. And that means that the spectral measures are the same for A and J. Okay, so what this transformation does is takes your matrix, takes it to a tridiagonal matrix, and keeps the spectral measure, keeps the sigma, which I write it as sum of Qi times delta lambda I. The Qi are these weights, right? These weights that I had explicitly before. So what is it? So there is this very nice fact that so these A's and B's, okay, which are the entries of the tridiagonal matrix, they determine these lambda 1s, lambda n's. They're just the spectral measure of the tridiagonal matrix, and the spectral weights Q. And you can see that this is 2n minus 1 parameters, right? And this is also 2n minus 1 parameters because the sum of the weights are 1. This is a probability measure. The spectral measure is always a probability measure. Okay, so it looks like that it's about the right thing. It sort of encode the same information, and that is true. This is a one-to-one mapping. It's a diffeomorphism, and it's beautiful. It's just basically, you can think of it as writing this measure in a different set of coordinates. And it's a simple transformation, but it's very nonlinear. Okay, and it's a beginning of many theories, including the theory of orthogonal polynomials and total lattice and scattering theory. Basically, many things that are simple in one coordinate system are hard in the other, so you do this transformation, and then you get something interesting. And of course, you can generalize this beyond finite measures. You can do infinite probability measures, or infinitely supported probability measures, or you can do even infinite measures. And there is a nice theory of canonical systems that de Branche sort of developed, and has a beautiful book called Hilbert spaces of analytic functions, which is somehow extends it to the right generality. But of course, there is much more work on this. I'm going to get back to this later. So, okay, so we have this bijection, okay, between these entries of the Jacobi matrix and the parameters of the measure, and And it turns out that if you put logs over here, then this is going to be, then this is up to constant measure preserving. So when you compute the Jacobian, it's going to be a constant. Okay, so that's nice, because you can put some measure here and you get some measure there. And you don't have to worry about the change of variables formula too much. So one of the measures that you can put here in these things is you take the exponential, you take some polynomial v, and you look at this exponential of the trace of v times the product of the b's. So this is nice because you see this is the product of the b's, and you can also write it in terms of the a's and b's. So this is really directly a density in terms of these variables. And here you can put this measure on the other side, okay, which is the same thing, but this exponential of the trace of v you can also easily express in terms of the lambda. So again, it's a nice measure here. And then there is a simple fact from orthogonal polynomial theory that these quantities on the right, this one here and this one there, are equal. Okay, so these two measures are exactly the same measures, okay, and in here and there. So this yields a lot of things. So basically, this lets you define the beta ensembles. So here is what Edelman and Dimitri proved, and we basically proved here now. Okay, that is the following. So if you take AI, so the coordinates to be AI of these normals, and the BRs are these chi's, but now there should be a beta there multiplying the index. Now they look like this. Then the eigenvalues, and you take that Jacobi matrix with these independent entries, then the eigenvalues have this joint density, which is again, that product shouldn't be there, but which is again just, this is the normal distribution and plus a Vandermonde. So this is, you must have seen, this is for beta equals 1, this is the joint eigenvalue distribution of the GOE, beta equals to the GUE, but it makes sense for general beta. And now you have a matrix model. This is the Edelman-Dimitri theory for this particular beta ensemble that, by the way, was introduced by Dyson in the 60s. So this is a Jacobi matrix model for that. And the QIs are independent of everything with the weights, and they have this Dirichlet distribution. So when you take V to be polynomials of degree 4, actually these AIs and BIs are not going to be independent anymore, but they're going to form a Markov chain. And you can guess what happens when V is of degree 5, in degree 6. So it's homework if you are interested in these things. So let me see. So when sigma has infinite support, then J is a semi-infinite matrix, and so you can still define this matrix J is going to be a semi-infinite matrix, an operator, and there are some examples. So when sigma is the semicircle, then the AI are 0 and the BI are just identically 1. And when sigma is standard normal, then the AI are 0 and the BI are square root of I. Okay, so if you look at the characteristic polynomial of the truncated matrix of this J, so it's a semi-infinite matrix, and you just look at the corner of it, then it's a fact that it's just the kth orthogonal polynomial for this measure theta sigma, which is the spectral measure of J at the tip as before. So you can this gives you a very nice fact. So you see these things, if you do them the other order, so instead of bi you rename them bn minus I, then you just have psi I here times the beta, and these things are going to be, these matrices are going to be nested. So for each n you get the next matrix. The n plus first matrix is, sorry, the nth matrix is the minor of the n plus first matrix, and so on. And you can take the infinite version. Okay, so this is just the semi-infinite J, where the AI have this distribution and the BI have that distribution. Then to this random semi-infinite matrix, there exists a random measure. Okay, so this random measure, we call that sigma beta, and we call this the beta Hermite measure. Okay, so it has this amazing property. So I just had to tell you because it's so nice, that if you take this random measure, so it's just a single measure, and you look at the nth orthogonal polynomial for this measure, and its distribution is exactly that of the beta Hermite ensemble for the n by n case. So for example, when beta is 1, then this is exactly the characteristic polynomial of the GOE. And so it's a single random measure on the real line that couples all of these things together. It's really what it is when beta goes to infinity, you can see that this goes to 0, the I goes to 0, and the BI, they just go to square root of I. Okay, so beta equals infinity case is really just the standard normal. So you can think of these measures as some noisy versions of the standard normal. And when you take the orthogonal polynomials, you get these beautiful random matrix ensembles. Okay, so there is a nice theorem of Breyer, Jonathan Breyer, that if you look at the Hausdorff dimension of this measure, then it's exactly 1 minus 2 over beta plus the positive part of that. So it's actually it says a little bit more. When this thing in here would be negative, then this measure is going to be a poor point measure. So it's just a bunch of points, and there are very nice connections to this, or actually to be explored to quantum gravity and SLE, where you also these dimensions also come up through the standard identification of kappa in SLE and beta. So that's another way you can take a limit. This J is another operator limit of your random matrix. Okay, it's a semi-infinite matrix, and what it provides you is this nice coupling of the various matrices, various ensembles together. Everything is encoded in a single measure on the real line. Okay, so that was, let's see, that was number 2, and I'm going to go to number 3 now. So it's a third limit. So this is sort of a different kind of limit, the stochastic Airy operator. So this was introduced and conjectured by Edelman and Sutton. And so the idea is the following. If you look at just this matrix, which is -2s on the diagonal and 1s on the off-diagonal, then you all know that this sort of discretizes the second derivative, right? So it's a discrete version. You could use it to compute second derivatives with your computer by plugging into some fine mesh and use this matrix instead of the second derivative. So you're hoping that your Jacobi operator, this J, which corresponds to the random matrix, also discretizes something. Okay, and so the question is, what is it that it discretizes? Well, it won't just be this, but something more subtle. So for that, you have to, this is some. Okay, so this B case, you have to see the asymptotics of this B case. So when k is much less than n, okay, then we're close to the square root, and you can expand in Taylor expansion near the square root. So this B case, they behave like square root of n minus k over 2 root n times plus some normal. Okay, so if you take your Jn, okay, you subtract it from 2 square root of n, which is actually the top edge of the spectrum empirically, right, from the Wigner semicircle law. So this is going to be something which is almost positive definite. It's not exactly, because there are a few eigenvalues hanging over, but it should be almost positive definite. Then what does this look like? So you can expand according to the entire matrix which we had above, right, this J, to this expansion, and you get this second derivative-like term, and then this term which comes from the expansion of the square root there, which is just a linearly growing term, and plus some kind of noise term. And so when you just look at it and say, well, if the scalings work out right, and they work out right exactly for one choice of n, which is when you zoom into a top part of the matrix, which is n to the 1/3 long, then you get an operator which reflects all these terms. And indeed, that's the case. You get this h beta, which we call the stochastic Airy operator, and it comes from 3 terms. A second derivative, a multiplication by x from here, and then a multiplication by a white noise term. And there is really no problem with defining this. You just think of this as distributions, and the operator this operator is perfectly fine, unlike some other ones. So this is what it looks like, and it acts on the L2 of the positive real line with Dirichlet boundary conditions. So you have to have B0 at 0. So this was the top edge. So we took this limit of this operator in this window of size n to the 1/3, and what it gave us is the limit of the top edge of the spectrum. So this operator has eigenvalues which are limits of the top edge of the spectrum. In particular, the lowest eigenvalue, I guess, yeah, so the top eigenvalue of minus h beta has this Tracy-Widom distribution, which is the limit of the top eigenvalue distribution of the random matrix. And to define this for general beta, we had to go through all this stochastic Airy operators, although for the classical beta, this was defined in many other ways. So this was, convergence was predicted by Edelman and Sutton, and we showed it with Ryder and Ramirez. And we also showed later, last year, a kind of universality. So for any polynomial which is uniformly convex, you have this as a limit for the corresponding beta ensembles. So this representation gives you a lot of things, and I will tell you what. So it gives you some tail bounds for the Tracy-Widom distribution, some very precise one, and also some finite versions. So even for the finite Jacobi operator, you can just imagine it as some finite discretization of this, and then you can apply the arguments that I'll show you a little bit about. And there's a very nice paper of Michel Ledoux and Brian Ryder where they do this. So they have good large deviation bounds or intermediate deviation bounds that are new even for the classical values of beta. You can also get Paul-Levé formulas quite directly from this. And you can also study low-rank perturbations. For example, stuff like you take the GOE with finite mean and questions like this. Okay, so let me give you, I'm actually going to give you another proof here. So the proof is a tail bound. This is actually precise asymptotic, so the other inequality is also true for the Tracy-Widom beta distribution. Okay, so the nice thing about this distribution is that it's this very thin tail, right? It's exponentially minus a cubed in one direction, and it's 3/2 in the other direction. So we can prove this one, and I give you, a two-line proof. Okay? So how do you prove this? This upper bound? Well, if the bottom eigenvalue is greater than a of this operator, right? That means that if you plug in any nice function into the operator, then the norm of this inner product will be at least a times the norm of f squared, right? That's just the Rayleigh quotient formula, if you like, or just because the operator is greater than a times the identity. So in operator norm, so that this is an implication. So this has to be for all functions that you can plug in there. Now, if we plug in a non-random f, so of course you can plug in random f's that depend on h, right? That's fine, because it's a random operator, you can test it with random function. But no, you can just plug in a deterministic function, okay? But if you plug in a deterministic function, well, what did we have in the definition of h beta? Well, just some derivatives and things like this, right? And the multiplication by white noise. So when you compute this inner product, it's just going to be a Gaussian. You just multiply, just doing a Gaussian integral of some fixed function. So this thing here is a Gaussian, okay, for every fixed function you plug in. So computing the chances of this being greater than something, is trivial. You just use Gaussian tails. So all you have to do is pick the right f. And I tell you what the right f is. Okay, this is the right f. So this is some solution of some variational problem. But you don't have to know the variational problem to verify this proof. Okay, you just plug in this f, do the computation, and you get the Gaussian tail bound, and it gives you this nice Tracy-Widom bound. Okay, so this is really a sort of two-line proof of some hard fact. And again, the Ryder can do this for finites and in all tails in all directions, and with Lord Demels, we did some more precise asymptotics of the right tail. With some, even we can compute the power of the polynomial that's in front of this expression. Okay, so I have a last 5 minutes. I'm gonna jump to my last operator limit. Okay, and the last operator limit is what happens in the box. So what if we zoom into the middle of this operator? So here is kind of a space. This is a picture from the clouds. There's actually a cloud here. So the story is this, right? If you just think about it in terms of number theory, right? So what should be true? So the Riemann-Zeta's functions by the Montgomery conjecture should converge to some process, which is this limit of the GOE eigenvalues, right? This is a theorem that there is some translation invariant process called the sine 2 process, where the Riemann zeta zeros should converge. This is the Gaudian-Medre theorem. Now, one way to prove the Riemann hypothesis with the branch tried is to construct some operator. It was actually an idea of Hilbert and Poya independently, so that the Riemann zeros will be, self-adjoint, and the Riemann zeros, shifted the right way will be its eigenvalues. So that's in the class because nobody knows how to do it, and the branch tried, and that didn't work so well. So the question is, well, to this thing there is an operator, and to this thing there is a conjectured operator. But what is the operator for this process? It's not known because they didn't take a limit of the operator, just took a limit of the eigenvalue distribution. So what would come here? Okay, so that's the question that I want to talk about in the last set, and this is we call this the Brownian Carousel operator, and I'll describe it in the last 2 minutes or something that I have. Okay, so what is it? So I have a path. So D is the unit disk, okay, the interior of the unit disk, and I have a path from 0, 1 to D. Okay, and it's such that at time 1 it goes to the boundary. Okay. Then I have this matrix which is basically built out of this B. It has some geometric meaning, but I'll skip that now because there's a geometric meaning of this matrix xt. But the main point is that this just depends on B. B is basically the parameter in this operator. Okay, and so the carousel operator associated to B is this operator. So first of all, it takes functions which go from 0, 1 to pairs of complex numbers, so vector valued functions. And what does it do with them? Well, it takes a derivative first, then it multiplies by the square of this time-dependent function, okay? And then it multiplies by the matrix J. So you can check that it's self-adjoint with respect to the right measure, and then there are boundary conditions you have to set what happens at time 0 and at time 1. And the interesting thing is that this is a canonical system in the sense of the branch. I mentioned this in the beginning, that this is sort of the generalization of this orthogonal polynomial story and this map. And also this is the canonical system is the kind of operator that the branch tried to show that the Riemann zeta function that fits the Riemann zeta function. And it didn't work here, but it works there, but it works here. So it's exactly the right kind of operator historically. Let's see. Okay. So this is the carousel operator, and okay, and yes, okay. So the Brownian carousel, the Brownian version is the same. You just take this B to be a specific path. So it's a path that satisfies this SD in the circle, and the interpretation of this is that this is hyperbolic Brownian motion. This factor makes it hyperbolic, run on logarithmic time. So this factor makes it logarithmic time. So that's what it is in words, but this is the SDE for the process that drives this thing. And the theorem is, of course, that the bulk limit, the bulk eigenvalues converge in distribution to the eigenvalues of this operator. And in fact, the matrix itself converges after the right conjugation. So how do you interpret this carousel operator? Well, if you write down the eigenvalue equation, this is what it looks like. So if the change in G, I rearranged it, is just lambda times this expression, and using the properties of X, you can write it like this. So it's minus lambda times J to the power XT inverse. Okay, so if you think of this as Möbius transformations, these are 2x2 matrices, then this is an infinitesimal rotation. J is an infinitesimal rotation around the origin, and J to the X is an infinitesimal rotation around B. Okay, it's a conjugation of the original J, so it's going to be an infinitesimal rotation, but around another point, and that other point will be B. Okay, so you have this path in the hyperbolic plane, or in the Poincare disk, or in the unit disk, and what you do is you move along this path, and there is a point in the boundary, which is G. The vector corresponds to a point after projectivization, and it moves around the boundary at unit speed. It's rotated at unit speed around this moving center. And then you get an eigenvalue if it ends up at the right place. And you can also use it by oscillation theory to count the eigenvalues. So this is a geometric picture that, just in terms of geometry, tells you exactly how many eigenvalues are there in an interval. And you can derive SDEs and study this, and we did that, proving some conjectures of Dyson. So finally, I just want to give you the punchline. And the punchline is, how do you prove this theorem? So I can, the proof is actually, it's kind of hard in the GUE case, but if you look at the circular ensemble, so random unitary matrices, then the proof is very straightforward, and I'll tell you how. So if you have a unitary matrix, I claim that there is a sequence B1 to Bn, which sort of parameterizes spectral measure, just like the A's and B's in the real case parameterize the spectral measure of the symmetric matrix. Okay, but this is kind of a new way to parameterize them, and it has this property that if you take this B, which is just a sequence of numbers, and make a path out of it by a piecewise constant path, then if you look at this carousel operator for this piecewise constant path, okay, then its eigenvalues are going to be exactly the eigenvalues of the unit matrix, just lifted up to the line. So they're going to be real eigenvalues. They're going to live on the line. You lift from the circle the eigenvalues of the unitary matrix. And if you take the circular beta ensemble, then the consequence of a theorem of Kilip and Nenchu is that BK is actually performs a random walk on the hyperbolic plane. Just a nice, ordinary, but timing homogeneous random walk. So it's somehow exactly a random walk. Everything matches, and it's really, really pretty. So it's not so surprising that when you do your scaling, the random walk converges to Brownian motion, and these operators will converge the way we want it to. So maybe that's how I end. Thank you for listening.
What happens if the O and U is generally distributed, not just uniform distributed?
Which one?
U and O in your is generally distributed.
Oh, this uniform matrix?
Yeah.
Yes. So this is a general fact. It's actually, if I can go back. Yeah, so this is a deterministic fact, actually, right? So you take any unitary matrix, then its spectral measure can be parameterized by these B's. Okay, there's no randomness in here, such that you get this kind of Dirac operator, whose eigenvalues are just the liftings of the eigenvalues of U, if you drive it with this path by this B. And then it's just the randomness only comes from saying, okay, if you take the U to be circular beta ensemble, then it's gonna be a random walk. If it's not circular beta ensemble, it could be anything. There are many cases where we can identify what this path does, and we can study them and take limits, including.
Formal proof also can get through if the U is generally distributed. Formally, you can U and O is uniform distributed, and then you prove that short proof in some stars before almost at the beginning of your talk.
Oh, at the beginning, you're thinking of something else. Yes.
Yeah.
Yes. Oh, I see. I know what you're talking about. Yes, just a second. So I'll show you that. Yes, so there was this proof of the semicircle law, right?
Yeah.
Yes, it's a very good remark. I wanted to say that. So we proved the semicircle law by saying that by getting this uniform distribution on the Z, right? So if they put a general polynomial V instead of the squares, okay, then the same proof will work, except this U is not going to be a uniform; it's going to be a different distribution. And so this gives you another way of proving the limiting, the analogs of the semicircles for general V, this kind of equilibrium measure that you get. This gives you an alternative proof. There are many proofs of that, but in that case it's not so easy to compute. It's very easy to compute here. So.
Yeah.
Any further question? Okay, the next speaker.